Chemical equilibrium was a concept that transformed the world in which we live in today. To get an idea of how it happened to be such a big and important topic, we have to go back to the early 20th century and start off with the assassination of Archduke Ferdinand and his wife, which was the triggering effect that led up to World War I. In order to begin the war, the Ottoman Empire had to overcome a problem in that they were being embargoed from the import of Chilean saltpeter, more commonly known as sodium nitrate. Sodium nitrate is a common component of gunpowder at that time in history. And if you are having an embargo where you have to import Chilean saltpeter from Chile, and you are completely blocked off from importing it, then you cannot fight a war. So the problem becomes, how do you get this sodium nitrate if you can't import it? And of course the answer is to make it chemically. So enter the scene of Fitz Haber. Fitz Haber was an Ottoman patriot who was working prior to the war of making ammonia, NH3. And he was making about 125 milliliters per hour of ammonia from nitrogen in the air and hydrogen gas. And by 1914, they had scaled up from 125 milliliters to 20 tons a day. Now, ammonia can easily be oxidized into nitrate, so the Ottomans had found a way of chemically synthesizing sodium nitrate from this ammonia which Haber was able to produce. So the question then becomes, why was Haber getting so little ammonia initially, and how did he scale it up to a production rate of 20 tons per day? Well, Haber initially was getting 125 milliliters per hour because of chemical equilibrium. The reaction involving nitrogen and hydrogen to produce ammonia appeared to stop without ever reaching completion, no matter how much time the reaction was given. Initially, they would see a change in the rates of reactions. They would see the increase of ammonia and the decrease of nitrogen and hydrogen, but there was always some reactants left over when this reaction seemed to stop. And what was happening was that the reaction was reaching what we call chemical equilibrium. Chemical equilibrium occurs when a reaction and its reverse reaction proceed at the same rate. It's essentially a bathtub that's being filled and drained at the same rate. So it appears nothing actually changes, even though things are still going on. Chemical equilibrium also has both product and reactant molecules present at equilibrium. One never completely disappears or is completely used up, which is why we can talk about reactions and their percent yield and say something like a 45% yield is a good thing, because chemical equilibrium may only let 45% of the reaction actually occur before the reaction is done moving. Now, when we're at chemical equilibrium, the reaction is still occurring. It's just there's no detectable change. So the molecules are still colliding with each other. They're still bouncing off each other. But for every reactant that's made, a product is made as well. So again, it's back to the analogy of the bathtub that's being filled and drained simultaneously. You don't see anything change, even though there are things going on. So the reaction is still occurring at chemical equilibrium. It does not stop. So when we write reactions involving chemical equilibrium, we use this reversible arrow. So we indicate the reaction is occurring in both the forwards and reverse direction. And this is the major change to how we write balanced chemical equations when we have equilibrium involved. We no longer have a one-way arrow. It's now become two-way. So how do we arrive at equilibrium? Well, chemically what we're going to do is we're going to consider the forward reaction of dinitrogen tetraoxide into nitrogen dioxide. And so if we take the rate law for this and we assume it's an elementary reaction, meaning we can write the rate law based off of the mechanism, then we arrive that the forward rate is equal to a rate constant Kf times the concentration of nitrogen or dinitrogen tetraoxide. We can then do the same thing for the reverse reaction, where we take those two nitrogen dioxides and react them back to dinitrogen tetroxide. And the rate for the reverse reaction is equal to a rate constant Kr times NO2 quantity squared. And again, we can write this because it's an elementary mechanism step. Well, we define equilibrium as when the rate of the forward and reverse reaction are equal to each other. And so we can set up an expression that represents the two rates being equal to each other. And then what we do is we isolate the constants on one side and we leave the concentrations of the reactants and products on the other side. And so what we ultimately end up with in this case is the NO2 squared divided by the dinitrogen tetraoxide is being equal to a constant known as the equilibrium constant, or capital K. And I believe I stressed this when we first talked about rate constants, in that they were always represented with lowercase k's, and equilibrium constants are represented with capital K's. And so if we go back and apply this to Haber's system, what we can see is that his equilibrium constant for the formation of ammonia is equal to the ammonia concentration squared divided by nitrogen and hydrogen raised to the third power. So here's one of the first important concepts about equilibrium and equilibrium constants, is that the equilibrium constant is really a ratio. It's a ratio of concentrations relative to each other, or it's a ratio of pressures relative to each other. We write the equilibrium expression as the products raised to the power of the coefficient in the balanced equation divided by the reactants raised to their powers of the balanced equation. So you can see NH3 is raised to the second power because in the balanced equation there are two ammonias that are involved in balancing the equation. Likewise, the nitrogen is raised to the first power because in the balanced equation there is a coefficient of 1 in front of it, and hydrogen is 3 because we have the coefficient of 3 of hydrogen in the balanced chemical equation. So everything ties into the balanced chemical equation. Unlike chemical kinetics, you can write an equilibrium expression by looking at a balanced chemical equation. So we generally explain and represent chemical equilibrium as a ratio of products to reactants raised to the power of which the coefficient is in the balanced chemical equation. And when we talk about solutions that are aqueous, we use brackets. And when we talk about gases, we use P to indicate that it's a pressure. And then we write the molecule that's in the gas phase immediately after that pressure. So, for example, in the bottom there where you see PD raised to the D, that capital D would actually be some molecule. So this is how we write equilibrium constants. Now, Haber was committed to helping the Ottomans win World War I, and so he was actually associated with developing chemical warfare during World War I. And his involvement with that program actually caused a great deal of distress for his wife, who ultimately ended up committing suicide because she saw the damage chemical warfare did to soldiers. Haber took the attitude that death is death by whatever means inflicted. So you're going to die, it doesn't matter how you die, it's just you're going to die, which is kind of a callous attitude. And yet despite that, Haber's work won him the Nobel Prize in 1918 after the First World War was over. And the reason he won the Nobel Prize, even though being involved with such a deplorable weapons program, is that his reaction for the making of ammonia was actually intended to be used for creating fertilizer which also needs nitrates. And if you can get nitrogen out of the air, which is free, then you can create ammonium, take it to a nitrate form, and nitrate is a very useful nutrient for plants. So it ended up revolutionizing the agricultural industry because we now had a cheap way of creating fertilizer. Nitrogen, up to this point in time, had always been the limiting reactant in plant growth, and you were limited to successful crops based off of how much nitrogen you had in your soil. This was no longer an issue, and so now farms were able to increase their production tenfold because they have access to cheap fertilizer.